And gosh, I am excited to have Larry Meinert joining us today. So Larry has an extensive career that it was so hard to pick which topic he covers for us today. But as he's worked as a consultant for major mining companies in more than 50 countries, he's probably seen more skarn deposits than anyone alive. So with his vast expertise, I cannot wait to get his insights on exploration for skarn deposits. So this is going to be an awesome session. I hope you all get a lot out of it. Please use the chat and we'll open up the floor at the end. And yes, thank you so much, Larry, for joining. It's amazing having you today.
I am tempted after that Magic Mike presentation to tattoo the word Skarn across my chest, and then sort of halfway through the talk, I could do the big reveal, but that might gross some people out, so I don't think I'll do that. I like talking about exploration for skarn deposits because it's one of the few areas where people can very quickly learn enough to be very dangerous. For some reason, skarn deposits seem to send many people shrieking and running for the hills because they view them as incredibly complicated and incomprehensible, whereas I view them as very simple and easy to understand, and that gives me a great advantage over all the shrieking people running for the hills. So in another 45 minutes, you will now know enough to be dangerous, and you too can tattoo the word Skarn across your chest. So we can start off and ask, why should anybody care about skarn deposits? And there's a lot of reasons. They're mined for many metals, the major ones: iron, copper, gold, lead, zinc, silver, tin, tungsten, moly. But there are skarns that have significant amounts of a lot of other elements. And basically every element in the periodic table could occur somewhere in a skarn deposit. And the reason for that is quite simple. Skarns represent a tremendous temperature and compositional gradient, usually between intrusion and carbonate wall rocks. And that gradient allows many different metals to be precipitated and concentrated. So skarns tend to be fairly high grade compared to other types of deposits. In addition to this cornucopia of elements from the periodic table, they're also quite abundant. There's several thousand skarn deposits described in the literature. On this map, I got red dots showing you the distribution of some of the major deposits, but there literally are thousands of deposits out there. Another reason for caring about skarns is they can be quite large. As an example, Antamina in Peru is about 2 billion tons with significant copper, zinc, and minor moly and silver. Okay, when I was initially working there, it was the world's third largest producer of concentrates, the third largest for copper, and the seventh largest for zinc. Okay, so for people who might claim that skarns are not terribly important or small or spotty, the numbers tell an entirely different story. These are significant deposits, and this deposit is in the lowest cost quartile of global production. So for economics, these things are really important. And if that doesn't get your attention, you've got the Erzberg district, which is the largest copper gold resource on Earth. When I was working there, there's more than 5 billion tons of ore, greater than 1% copper, close to a gram of gold. And this is really important. There's more ore in skarn there isn't in porphyry. Okay, there's also mineralized porphyry there, and a lot of the world's literature describes this simply as a porphyry deposit. Okay, and there is indeed mineralized porphyry. I'm not, denying that, but there is more skarn there, more metal in skarn than there is in all the porphyry put together. So a more accurate description would be this is a skarn district that happens to have some porphyry. Okay, but you won't see that in the world literature. So just one more example of why you need to know something about skarn deposits. So let me go through a little bit of terminology just to get us all on the same page. And as Magic Mike now understands, we've got both endoskarns and exoskarns. Okay, and that simply refers to whether the alteration is affecting igneous rocks or sedimentary rocks. Okay, if it's affecting igneous rocks, we call it endoskarn, and if it's affecting the sedimentary wall rocks, we call it exoskarn. A lot of people take this as a genetic terminology, meaning endoskarn from the causative pluton. But in many cases, we don't know what the causative pluton is. And we're in porphyry districts, you might have a dozen different intrusions, each one of which is adding something to the mineralization budget. So to talk about which one is the cause of the Pluton is somewhat of a semantic exercise, doesn't really have a lot of meaning. So I like to use these terms in almost everything I'm going to describe in this talk in a descriptive sense rather than a genetic sense. So we describe the rocks, what we can map in the field, and that's how we proceed. The most useful classification of skarn deposits, certainly for economic geologists, is based upon the major economic metal. Okay, and the 7 major skarns out there are iron, copper, zinc, gold, tungsten, tin, and moly. Okay, and the way we define this is that that is the major metal that is being mined from a particular deposit. You'll always have a series of byproduct metals, okay? And if you go to the Chinese literature, they tend to list everything under the sun, whether it's economic or not. So you'll see a title that says the XYZ deposit that is a iron, copper, zinc, gold, tungsten, tin, moly, rare earth element, uranium deposit. And that, of course, is not terribly useful because what you really want to know is, okay, if you're going to mine this, you have to mine it for X. And so these 7 categories are the major categories, and every single skarn deposit in the world can be classified according to what you're going to mine it for. So even though most copper skarns will also have byproduct gold, silver, possibly other metals, unless you mine the copper, you can't mine it. So that's the basis for classifying skarns. So throughout this talk, when I talk about copper skarns or tungsten skarns, I'm talking about the major element that's being mined there. And if you didn't mine it for that, you couldn't mine it at all. One thing that's worth commenting on is the presence of magnetite, because a lot of people get caught up with, well, there's magnetite in the skarn. What does that mean? Okay, it doesn't mean much. Magnetite comes out very easily, particularly if you have some magnesian wall rocks, in which case you'll get very abundant magnetite. So unless you're mining the deposit for iron, and iron skarns, not surprisingly, have major amounts of magnetite in them, magnetite by itself is not terribly diagnostic or important. It obviously has a strong geophysical signature, so it's not that it's unuseful, but it's not important in terms of understanding the skarn itself. So let me take you through a couple very simple processes. So this is Geology 101. So anybody who's ever taken a geology course in their life has certainly experienced the things I'm going to talk about. So none of this is very complex. So on the far left side is a stratigraphic column with typical rock types, limestone, shale, sandstone. And on the right side of that left part of the figure is the metamorphosed equivalent of that. So limestone gets recrystallized to marble, sandstone to quartzite. And basically that's just a recrystallization, a coarsening of the grain size. We're not changing the composition. We're not bringing anything into or out of the system. We're just changing the texture of the rock. Things a little bit more complicated if we have impure carbonate rocks, like a silty limestone, in which case we'll start developing wollastonite, the reaction of the calcite plus quartz to wollastonite. And more complicated still if we have a calcareous shale. Now we've got lots of different elements, and so we'll form calc-silicate minerals during straight metamorphism. What's important is that all these things I'm describing are simple metamorphic reactions. Unless we had a previously existing ore deposit, we have zero potential for forming an ore deposit. We're simply recrystallizing things, changing the mineralogy. Okay, things are a little bit more complicated when we have contacts between different lithologies. And what I've blown up on the right side, labeled as B on the left side, is the contact between a limestone and a shale. And you can see that elements are moving from the limestone towards the shale and from the shale towards the limestone. And that ends up giving us a zoned skarn assemblage that we refer to as a reaction skarn. Okay, and that's a descriptive term because the skarn is forming from a reaction between these two lithologies. So the calcium is moving from the marble towards the shale, and the mineralogy, the most calcium-rich phase wollastonite is closest to the marble. That's where the calcium is. The most silica-rich phase, pyroxene, is closest to the shale. That's where the silica is. And garnet, which is intermediate in both calcium and silica, is in the middle. So reaction skarns, again, are a metamorphic product, and they reflect the rocks that are there. So this is mappable and interpretable in the field. And I go through all these early metamorphic features because they're going to have some of the same minerals that we'll see in the mineralized skarn, but they have zero potential for mineralization. So being able to distinguish these different things in the field is quite important. In other words, garnet here and garnet there could mean totally different things. And if you don't understand the difference, then you go, oh, skarns are so complicated. I have no idea what to do. Okay? But if you do understand these things, you say, oh, well, that's just the metamorphic garnet, and we don't need to worry about that. That's not going to be useful for exploration. Okay, we'll get things a little bit more complicated. The same stratigraphic section, now we run a big fault up through it, and we have fluids moving around just due to normal geothermal gradients, not necessarily related to an intrusion. And we're going to start moving things around even more, not just from the contact between the marble and the shale, but up along faults. And so we'll develop all sorts of calc-silicate minerals, some of which are cross-cutting other features because these fluids moving around. This is still a largely metamorphic process. We give a different word to these. We call it skarnoid because it's largely metamorphic, but things are moving around. Again, we can identify these quite easily in the field, and this is what it looks like in the field. Okay, this is just a bedded carbonate body that originally had layers of shale and limestone, and they are forming reaction skarns along each and every one of those layers. But in detail, you can see along the cleavage plane that garnets forming, cutting across the bedding planes. So all of this is a largely metamorphic process. Even though this rock is probably 50% garnet, this again has zero potential for mineralization. And so knowing that this garnet's different than other garnet is step one in exploration. It's just a close-up view of some of those layers, and it can be quite coarse-grained. You can see individual garnets the size of marbles there going along some of the shale beds, the reaction between the shale and the limestone. And this is just an illustration of what's going on at a mineralogical level. So in the upper part of this diagram, we have disseminated little garnets, and on the right, and labeled A, these are metamorphic garnets that were nucleating on a little pelloid or a fossil fragment of some sort and forming little garnets out there in the limestone. It's quite often that they have these very murky cores in thin section. And as more fluid flows along some of these bands down there where that coin is, and in B, you can see the murky cores now being overgrown by clear rims. So fluid is moving around, but this is all still a largely metamorphic process, whereas the metasomatic skarn that is going to be mineralized looks like C down there in the bottom. Totally different petrographic characteristics and much different field identifiable characteristics. Okay. Once we bring an intrusion into the picture, and here I've brought the magma right up along that fault in the previous diagram, and we allow it to crystallize and exsolve a hydrothermal fluid, and for right now, we'll just treat that as magic. Poof, out comes the hydrothermal fluid, and that fluid is swamping the rocks surrounding it, giving us a zoned skarn that is zoned relative to the intrusion. So we have an innermost zone that we could call endoskarn, where it's altering the intrusion itself. And out in the exoskarn, we have a proximal zone rich in garnet, more distal zones rich in pyroxene, and out near the marble front, we actually get a zone of elastinite. So this zonation in skarns is really, really important. It allows you to tell where you are in the system, what direction you want to go towards the intrusion, what direction you want to go towards marble, and given various models for different types of skarns, you can figure out where the ore zones would be within the zonation pattern. So let me make this very clear. Every single skarn deposit on Earth is zoned. Okay, for people who say, oh, I worked on a skarn, I didn't see any zonation. Well, that says something about you, but not necessarily about the skarn. Okay, so let me repeat this. Every skarn is zoned, and it has to be because of the tremendous thermal and compositional gradient between the intrusion and the wall rocks. And understanding that zonation, being able to map that zonation is really, really important for exploration. So let me just take you through this step by step. So we've got a magma intruding up, and it's heating up the rocks around it. So we have a classic metamorphic isograd, a thermal aureole around the magma. And this is before the hydrothermal fluid comes out. So we're just heating up the rocks around it. And as it intrudes further into the stratigraphic section, we can see that the metamorphic aureole is relatively small at the top of this diagram in a relatively shallow environment. Okay, and down near the base of this, and I purposely have the metamorphic aureole going off to the side of the diagram. I don't know if you can see my little arrow, but it goes way off over here. So in a deeper environment, the metamorphic aureole will be very, very large. Okay, so by shallow and deep, shallow is within a couple kilometers of the surface. it's hard to get a major igneous system within, say, a kilometer of the surface without blowing the top off it. Okay, and by deep, we're looking at 10, 15, sometimes even 20 kilometers. And this has a huge effect upon the metamorphic oriole and the subsequent skarn that'll be coming. Because if you are at a depth of 10 or 15 kilometers, you will have a geothermal gradient that those rocks started off life at 300 to 400 degrees before the magma even got close to it. So then if we have a large body of magma, particularly if it's a large batholith, like I've shown here in the bottom of this diagram, it's going to heat those rocks up to 5, 6, 700, maybe even 800 degrees, which means that everything that could be metamorphosed will be metamorphosed. All the reactive carbonate will be used up. All the original pore space will be clogged up by metamorphic reactions, and it's going to be very difficult to get fluid to move through that. In contrast, in the shallower environment, we've got a relatively small metamorphic oriole. The rock started off relatively low temperature, maybe 50, 100 degrees, and we've got a relatively small igneous body. So when the hydrothermal fluid comes out, it's going to overrun this very small metamorphic oriole, and it'll look something like this. So now magic has happened, boom, out comes the hydrothermal fluid. And in the shallow environment, the black, which represents the mineralized skarn, is now overrunning the original metamorphic oriole. And again, it looked like that before. And you can see that some of the skarn forming fluids are getting into unmetamorphosed rocks. And this is really important in terms of the ability to precipitate metals and the size and the geometry of the skarn deposit. Much more potential for a laterally extensive skarn, whereas the deeper environment is going to be a thin, narrow zone plastered up against the side of the intrusion, because it's very hard for those fluids to move laterally away from the igneous rocks, because they're totally within the metamorphic oriole. All the rocks have been metamorphosed, heated up, clogged up, all the pore space is gone. So you have relatively thin, narrow skarn zones totally within the metamorphic oriole. And then finally, what heats up must eventually cool down. And so you have high temperature minerals like garnet and pyroxene that when they're in contact with lower temperature fluids, say 300 degrees, 350, the garnet and pyroxene aren't stable, and garnet alters to things like epidote, pyroxene alters to things like amphibole and chlorite and clays. And this is what we call retrograde alteration. So prograde alteration is the heating path, where things are getting hotter and we're forming the characteristic skarn minerals, garnet and pyroxene. And the cooling path, we retrograde that, we alter the garnet and pyroxene to lower temperature assemblages. And that's where most of the metal is coming out. Not because there wasn't X, copper or tungsten, in the fluid at high temperature, but it's difficult to get those metals to precipitate at 500 or 600 degrees. As the temperature drops, the solubility drops, and that's where most of the metals come out. So a lot of the metal is coincident both in time and space with retrograde alteration. And all this is easily mappable in the field. So I talked about zonation before. This is a simple cartoon of what zonation looks like. And it's also illustrating one more complicating factor, and that is oxidation state. Now, a lot of geologists don't spend a lot of time thinking about oxidation state, but you need to for most deposits and certainly for skarn deposits. So what I mean by this, I'll start with the igneous rocks. Okay, a very reduced igneous rock is going to have ilmenite as the main iron titanium phase. And as it gets more oxidized, we'll get magnetite, leading to the relatively common Japanese classification of I-type versus S-type, magnetic versus non-magnetic intrusions. And as you get more oxidized still, you'll get titanite. And the really most oxidized intrusions are hematite stable intrusions. Most of the porphyry copper deposits in the world are hematite stable plutons. And we know that because when we see erupting volcanoes that are basically blowing the top out of what could have been a porphyry copper deposit, we see hematite and various oxidized forms of sulfur, sulfates, such as anhydrite and gypsum, being blown out of the top of things like Pinatubo. So we know for a fact what the oxidation state of those is. If we look at the wall rocks, we have the same gradient of oxidation state. A very reduced wall rock would be a very black carbonaceous, might even have graphite in it, limestone or shale. And a very oxidized will be white, have very little carbon in it, certainly no graphite. So we now have two end members. We could have a reduced or oxidized intrusion. We could have a reduced or oxidized wall rock, and the skarn is going to reflect the combination of those two, the interaction of those two end members. So what do we see in the deposits? Well, garnet, most of the iron is present as ferric iron, Fe plus through, the oxidized form. Pyroxene is mostly the reduced form of iron, Fe plus 2. So if we have a very reduced system, reduced intrusion, reduced wall rocks, we'll have very pyroxene-rich skarn. If we have very oxidized pluton and very oxidized wall rocks, we'll have a very garnet-rich skarn. So the garnet-pyroxene ratio, this mappable zonation we see in the deposit, will vary as a function of the overall oxidation state. So this allows you to start teasing out who did what to whom. So I look at the skarn, I look at the mineralogy. Is that consistent with what I see for the intrusion and the wall rocks? And if not, then that's a pretty good clue that that intrusion didn't do this, because it would have formed a different mineralogy if it had been present. So the zonation that we see in most skarn deposits is a mappable garnet-pyroxene ratio going from garnet-rich close to the intrusion and pyroxene-rich further away. The garnet color changes systematically from very dark, usually red-brown colors close to the intrusion, getting into various lighter shades of brown and green and yellow as you go further away. Pyroxene does the opposite. It's very light in color, close to the intrusion. It gets darker in color due to the presence of iron and manganese in the pyroxene. So I'm greatly simplifying the mineralogy, but these are mappable features in the field. We can map the garnet-pyroxene ratio, we can map the garnet color and the pyroxene color, and when you have more detail, you can actually do compositional analyses on this to figure out where you are in the system. Okay, if you have totally drilled out the deposit, well, then you're not terribly concerned. But if you've only got part of the deposit, or part of it's been faulted off, or part of it's covered by younger alluvium or overlying volcanic rocks, being able to work out the zonation is really, really important. And it's fairly easy to do as long as you understand mineralogy and can recognize them. So let me give you examples of this. So this is a very reduced system. This is the Headley gold skarn system in British Columbia, a very reduced stock, the Toronto stock. And by reduced, it's an ilmenite series pluton, no magnetite, no hematite. You can also look at iron oxide ratios by a whole rock analysis. But trust me, it's a very reduced stock. And the wall rocks also are very carbonaceous, so very reduced wall rocks. And so the total amount of garnet is very small. You can see a little bit of garnet, that brown color close to the stock. But the vast bulk, 90% of the skarn is very pyroxene rich, all the green colors. And in gold skarns, in general, the ore zone is out in the most iron-rich pyroxene because it's very reactive. So being able to work out this zonation also tells you where you'd want to go to look at for the gold. And let me bring this back to exploration. If you don't understand skarn systems in general and gold skarns in particular, you're probably going to go out there and sample the garnet because it's very resistant to erosion. So your outcrop's going to be garnet. And you go out there and you sample the garnet and you analyze it and you say, well, there's no gold here. Let's walk. This is not important. If you understand the mineralogy, you know that's the last place you want to be. You need to go find the very iron-rich pyroxene, which is going to be very easily eroded. So it'll probably be down in a gully somewhere with no outcrop. So knowing what to sample and where to go is just a basic understanding of skarn deposits. This is what the very proximal garnet pyroxene zone looks like at Headley. The garnet color is a fairly pale brown. The pyroxene, even though we're very close to the intrusion, is a medium green in color. And the overall garnet pyroxene ratio here is a little bit less garnet than pyroxene, but we're right next to the intrusion. So this is what I mean by a very reduced system has much less garnet and much less proximal looking garnet than you would see in an oxidized system. As you go further away, you lose the garnet altogether. The pyroxene's now dark green in color. And even though you can't see it, I like to bring this rock to me when I'm teaching short courses and pass it around the group and ask everybody to think about, if you found this rock in the field, what would you be thinking about? Make a long story short, this rock assays 20 ounces per ton, over 600 grams per ton gold, even though at the hand specimen level, you can't see visible gold. So unlike orogenic systems where you quite often see visible gold, you don't in this rock, even though it's extraordinarily high grade. At the thin section level, yeah, you see lots of gold. Okay, looking at the other end of the spectrum, these are very oxidized rocks. On the left is a magnetite-bearing diorite porphyry from a prospect in the Philippines. And the wall rocks are this conglomeratic limestone. This would be the outer reef facies, carbonate stratigraphy. And the mud in this conglomerate is all oxidized, very iron rich. You can see the sort of reddish color to it. So we have an oxidized intrusion, oxidized wall rocks, and this is what happens. It's almost all garnet. So close to the intrusion, it's a dark red-brown garnet color. And as you go further away, you get a brownish color and finally yellow-green and yellowish garnet. But it's garnet close to intrusion. It's garnet all the way out to the marble. And the pyroxene's only present at the thin section level. So this is what I mean by an oxidized system. And this is the typical color zonation you might see in a skarn deposit. Some other causes of variation are things like the oxidation state of the wall rocks and the composition of the wall rocks. So the left-hand diagram has a magma intruding up along a fault, which magically separates reduced rocks on the left side from oxidized rocks on the right side. And then going vertically, we have three different compositions: dolomite, limestone, and a calcareous siltstone. And you can see different zonation patterns. Let's just look at the limestone part of this. That's the middle horizontal layer. And on the right side, the oxidized side, we see a very large proximal garnet zone. That's the G. A relatively small distal pyroxene zone. That's the P. And a little bit of willastonite out towards the marble. That same intrusion with the same hydrothermal fluids in more reduced carbonate rocks on the left side as a much smaller garnet zone, a much bigger pyroxene zone, and still willastonite out towards the marble. And notice that the entire skarn is smaller, about half the size of the skarn in the limestone. This is strictly controlled by the oxidation state. So let me briefly explain why that is. Anytime you form a calc-silicate mineral, you have what's called a decarbonation reaction. So the very simplest one would be calcite plus quartz going to willastonite plus CO2. And that reaction is going to give off CO2. And unless you can get that CO2 out of there, it's going to shut down the reaction. If you've got carbon in the wall rocks, you have to oxidize that carbon to CO2 and get rid of it before you can form any of these calc-silicate mineral reactions. So the presence of the carbon will slow down or shut down the skarn forming reactions. And that in a nutshell is why the skarn in the reduced rocks on the left side is much smaller than the skarn on the right side. And then on the overall right side of this diagram is just looking at some structural considerations. In most districts, there's a particular lithology that is more favorable for replacement. We never know exactly why it is. It might be grain size, it might be reactivity, but we never really understand it. But we know that systematically in that district, the X formation, it might be the Escabrosa formation in Mexico or the Naco formation. And that is the formation that's going to get formed into skarn prior to anything else happening. And then when you have various structures, whether it's vertical, allowing fluid to move up along a contact, faults allowing things to move out. So structural control on fluid movement is quite evident in these deposits, easily mappable in the field. So let me take you through several different skarn types to illustrate some of these features in the field. And we'll start off with the tungsten skarns because they form in a very deep environment of formation. And I'll use the same terminology for all of the different deposits. So in terms of tonnage and grade, these tend to be relatively small. The largest in the world is about 60 million tons of 1% tungstate. Okay, compared to a copper skarn or an iron skarn, which will be in the hundreds of millions to billions of tons. These things are tiny, but that's where the tungsten occurs. The composition of igneous rocks are calc-alkaline, granodites to granites. So nothing particularly special about them. So calc-alkaline is what you'll get in any subduction zone anytime you have convergent margins. The geometry of the igneous systems, these are coarse-grained batholiths, often with pegmatites and megacrysts. All this due to the very slow cooling of these large igneous bodies at depth. If they were within a couple of kilometers of the surface, they'd cool much more quickly. They'd be porphyritic, they'd have chilled margins, but not down at 10, 15, 20 kilometers. There you have big batholiths, coarse grain, equigranular deposits, pegmatites, etc. The alteration of igneous rocks is basically absent because the hydrothermal fluids are also high temperature. They're stable with the igneous rocks, so you just don't see much alteration at all, whereas the metamorphic aureole is huge. It's both extensive in size and has high temperature mineral assemblages. Okay, lots of skarnoid and reaction skarns and all the things I described early on. So here's an example of one of these. This is the Sierra Nevada batholith in California. large batholithic bodies, kilometers in scale, and surrounding it is a very large and high-grade metamorphic aureole. Okay, the various colors on this map outside of the intrusion, you can see the various browns. Those are assemblages with things like biotite, silmonite, almandine that indicate temperatures of 600-700 degrees and pressures of 2 to 3 kilobars. And those metamorphic zones go for kilometers away from the intrusion. In contrast, the thickness of the skarn is less than the black line I use for the contact of the intrusion. It's that little yellow arrow pointing to the skarn locality. So the whole skarn is within that black contact. So you can see the size of the metamorphic aureole surrounding that skarn occurrence. This is what it looks like in the field. The Morgan Creek granite area on the left, marble on the right, and that dark area vertically oriented right there at the contact is the skarn. This is the Pine Creek tungsten skarn, the largest tungsten skarn in the United States. You can see a person there for scale. And you're probably thinking, well, how the hell can that be the largest tungsten skarn anywhere, much less the United States, if what I'm looking at is what I see? And it's, 5 meters wide, roughly. Here underground, at most, it might be 10, maybe 20 meters wide. But the reason why it's a large deposit, it's been mined vertically over 3.5 kilometers and along strike for more than 4 kilometers. So this is what I mean by a thin, narrow skarn zone right at the contact of the intrusion, because the fluids can't really move laterally away from it due to the high degree of metamorphism of the surrounding rocks. This is what the skarn looks like. This is a hand specimen, but we could do the same thing for a mine map level. We've got 2 main minerals here. We've got garnet, various shades of brown, red-brown, and pyroxene, the dark green color. And you'll notice not only do we have garnet and pyroxene sort of disseminated in the middle of this, we've got some very clear cross-cutting veins of garnet. They're slightly later than the main skarn. And because the main ore mineral scheelite fluoresces, it's pretty easy to see what's going on here. So all those little bright blebs, that's scheelite. And so in the main skarn, that's probably 1.2% tungsten. And where these garnet veins cut through it on the right and on the left, all the tungsten's been dissolved and stripped away. That's because scheelite has a solubility minimum, so that you need to be able to get the scheelite precipitated at high temperature before these lower temperature garnets come in and dissolve all the scheelite away. If we go to the shallow environment of formation, copper skarns, these are now much, much bigger. Okay, typical deposits are 500 million tons, roughly 1% copper, depending on the mining method. In general, underground mining being more selective will give you about twice the grade and about half the size of the deposit. So big open pits, of course, are much bigger and lower grade. Igneous composition, pretty similar, chalcocline, diorites to quartz monsonites, not quite as evolved as the tungsten skarns, but nothing really specialized for either one of them. The main difference is the depth of formation. And we see that in the geometry of the igneous rocks. The things are porphyritic stocks and dikes, medium grain to porphyritic. We don't see the large batholiths. We don't see the large megacrysts, certainly not pegmatites. And the stocks and dikes are typical of the shallow environment of formation. And because the fluids coming out are not in equilibrium with the igneous rocks, we see abundant alteration of the igneous rocks. Typical alteration types that you'd see in a porphyry copper deposit, K-silicate, sericitic, propylitic alteration. And epinode endoskarn is very, very common because, again, the fluids are picking up lots of calcium from the carbonate wall rocks, but they're not in equilibrium with the intrusion, so they're altering it. The metamorphic aureole is variable in terms of size, depending on how much water is flowing around, but it systematically lacks the high temperature mineral assemblages we see in the tungsten skarn environment. Here's a map of an occurrence. This is the Santa Rita deposit, about 1 billion, 1.5 billion tons total of skarn and porphyry in New Mexico. Okay, the intrusion now is much smaller. You can see the entire thing is slightly less than 1 kilometer across, and the skarn is much more extensive. There are zones, that red color, where you have massive skarn for a continuous kilometer away from the intrusion. In contrast, the metamorphic aureole, such that it exists at all, is locally within meters, tens of meters of the igneous contact. And the 2 dashed lines here, the inner one is the occurrence of any calc-silicate minerals whatsoever, not 700 degrees. but any reaction. And then the outer dashed line is the outer limit of bleaching. And what I mean by bleaching is simply the oxidation of carbon, driving it off as carbon dioxide. And so this is a very easily mappable feature in the field. The next picture I'm going to show you is a rock between those two dashed lines. So we have chert nodules. This is the Escabrosa limestone. And there's bleaching around each one of the chert nodules. But if you look at the contact of the chert nodule with the carbonate rocks, there's no wollastonite developed at the contact because we're outside of this heavy dash line, which is the outer limit of calc-silicates. So we're in this region here. And if we went further this direction, we'd lose the bleaching. If we went closer to the intrusion, we'd start picking up wollastonite along the contact. So again, this is a mappable zone feature in the distal regions of the skarn, not because there's going to be mineralization here, but this is the larger bullseye that allows you to figure out where you are in the system and what direction you'd want to go. Okay, so this is in the main pit at Santa Rita. The light color material are the porphyry stalks, cupolas coming up into the strat section. And basically everything in the far wall of that pit, all the dark material, is 100% skarn replacement of the rocks. Not a thin, narrow zone along the intrusive contact like in the tungsten skarn. Everything for more than a kilometer has been converted because we've got so much fluid coming out and everything's been converted to massive skarn. Here's another example down at Cananea in Mexico. You can see the stratigraphy dipping off to the right. You can see individual beds in there. Everything's been converted to monomineralic garnet skarn. So what used to be limestone, what used to be shale, the fluid says, I want garnet. And so everything's been converted to garnet. This is the core of the system, the proximal, very garnet-rich zone because it's an oxidized copper skarn system. This is what the zonation looks like in the skarn deposit. In a very proximal zone on the far left, you can see this dark red-brown color. That's very typical. It tells me exactly where we are in the system. This is very close to the source of the fluid. As I move further away, I get more of a brownish color. On the far right, I'm starting to pick up various browns. As we go further away, now it's getting a very light brown on the left side, sort of a greenish brown in the middle. And on the right side, we're now starting to get yellow and green colors and the beginning of pyroxene interstitial to the garnet. So this is what I mean by the zonation of the skarn. It's mappable in the field. It's telling you about the oxidation state of the system. It's telling you what direction the intrusion is, what direction the wall rocks are. And when you look at the genetic model for a copper skarn, you know exactly where the main ore zone, the peak copper, is going to be within this zonation sequence. Okay, this is what retrograde alteration looks like. Okay, before I talk about those nasty veins cutting through it, notice that we have garnet and pyroxene. I've labeled them here for you so you know exactly what they are. So now we can get some idea of where we are in the system. So what color is that garnet? It's a fairly dark red-brown color. What color is the pyroxene? It's fairly pale color, fairly light tan. So all this is telling us that we're in a proximal zone. And this one is about 200 meters away from the main intrusion of a big billion-ton system. But the reason I'm showing you this picture is that we've now got these lower temperature veins cutting through it, and they give us a snapshot in time of what retrograde alteration looks like. So you can see these various veins. The alteration is lower temperature minerals with abundant sulfides being precipitated. So I'm going to show you a pair of thin sections. We'll first look at nice fresh garnet in here, and then we'll move over a few centimeters to where one of these veins is cutting through it. So first, the fresh garnet. This is uncrossed nickels. You can see the dodecahedral shape of individual garnet crystals. This whole thing is garnet, 95% garnet, pretty fresh. You know, it's fractured up, but this is all garnet. We move over a few centimeters away, and boom, all the garnet is being retrograded to a mixture of epidote, the greenish color, amphibole, probably some chlorite, and abundant sulfides and oxides. You can still see the remnant shapes of the garnets, but they're completely gone. Okay, so this is what I mean by retrograde alteration. Okay, so that was up here in the garnet. We'll look at the same thing for pyroxene. We'll look at a nice fresh pyroxene, move over a few centimeters and see what happens when this retrograde alteration comes through. So this is cross nickels now, so you have bright colors, but you can see the rectangular layers of the pyroxene, nice fresh looking pyroxene. Move over a few centimeters, boom, it's all altered to mixtures of amphibole, chlorite, and an iron-bearing montmorillonite clay called nontronite that's very common in skarn deposits. The texture is still there, but the garnet and pyroxene are completely destroyed. Okay, the last skarn type I'll walk you through are the zinc skarns, because these form distal to the causative magmatic system. And they're really, really useful for exploration because they are the distal fringe of what could be really large deposits. They are very high grade, but usually quite small. The biggest in the world are about 50 million tons. But you can see the grade, 15% combined lead and zinc, 150 grams silver. So they can be economically important in themselves, but a lot of their importance is just due to their exploration vector to much larger systems. Using the same terminologies I did for the tungsten and copper skarns, the igneous composition ranges from granodiorite to granite to unknown. And I don't mean unknown in the sense of no intrusion. I mean, we don't know where it is. Okay, and I'll show you a little cartoon illustrating that in a second. For the geometry of these rocks ranges from batholiths to stocks to dikes to unknown, because we don't know where the intrusion is. And the alteration of the igneous rocks, if there are any, is extensive because the fluids are now greatly out of equilibrium with the magmas. And so you have extreme alteration, usually zone skarn going into the intrusion and into the wall rocks. And the metamorphic aureole is basically non-existent. A little bit of bleaching and recrystallization, but no high temperature minerals whatsoever. So this is the mental image of what's going on. We've got an intrusion, fluids coming out at relatively high temperature at the contact, say 600 degrees, and we'll have either a tungsten skarn or a copper skarn, depending on the depth of formation. If we take that same intrusion, those same fluids, and channel them out away from the intrusion, either along a fault or stratigraphic contact, before those fluids encounter carbonate rocks, and the fluid is now cooled down to, say, 400 degrees, okay, we'll have a much different skarn assemblage and much different mineralization. We'll see lead, zinc, and silver out there instead of the copper and tungsten, which were either dropped out close to the intrusion or more likely dribbled out through the country rock as the fluids moved along the path out to the carbonates. Again, carbonate is extremely reactive, so it's very good at pulling everything out of the fluid if the fluid gets to the carbonate rocks. Okay, so this in a nutshell is why we see the different metals in these deposits. Okay, it's just looking at the solubility of iron, copper, zinc, and lead as a function of temperature. And for any one of these elements, the solubility drops as the temperature drops. And at any given temperature, we'll get iron and then copper, then zinc, then lead coming out. So if we take any hydrothermal fluid and we take it through a temperature gradient, we'll eventually drop out all these metals. But if the vast bulk of the skarn is forming at 300 to 400 degrees, it's going to be dominated by lead and zinc. In contrast, if it's forming at 400 to 500 or 600 degrees, then we'll see iron and copper, and the lead and zinc will go out somewhere in the more distal, cooler parts of the system. So let me walk you through one of these. This is the Paymaster deposit in Nevada. There's a little trench, roughly the size of the room you're probably sitting in, so it's not a big deposit at all. And the closest igneous rock is poking over the horizon. Okay, and it's up there in distance. It's about 2 to 3 kilometers away. There's an aerial photograph showing a very clear lineament going from there towards us. And it's going through a clastic sequence, basically turbidites. And the very first carbonate horizon is where we are with this trench. And that fault that you can see in the trench is what we think is the extension of that lineament we can see on the surface. Of course, it's hard to prove that the fluids came from that particular intrusion coming out here, but that's the only intrusion in the area. This is the first carbonate rock that those fluids had a chance to interact with. And the mineralogy of the skarn tells us that we're in a very distal location. So let's jump into the trench. There's the fault itself. On the left side, the carbonate rock is been converted to garnet, pyroxene, skarn. The right side, which are clastic rocks, basically sandstones and siltstones, are bleached, but there's no calc-silicate minerals because there's no carbonate there, because we're in fault contact between two different lithologies. As we move away from that fault, oops, wrong way. Okay, this is what the skarn looks like. So let me be very careful in the terminology. This is the most proximal part of this skarn in a very distal location. So it's proximal in the sense that we're right next to that fault, but we're 2 kilometers or more away from the source, from the intrusion. So the mineralogy here is Garnet, much less than pyroxene. The garnet's pale in color. It's not that dark red-brown I was showing you before for proximal locations. And the pyroxene is already a dark green, even though we're right next to the fault. So even though this is a proximal location, we're looking at very distal mineralogy. If we knew nothing else, we'd look at this and we say, well, we're not close to the intrusion. We wouldn't see this mineralogy. So the intrusion must be somewhere far away. And as we move away from the fault, we see the garnet drop out very quickly, and the pyroxene gets very dark in color, and that's due to the increase in iron and manganese in the pyroxene. And if we go out to the end of the trench, the whole trench is about 15, maybe 20 meters at most. This is the skarn directly in contact with marble. You can see the black coating on the skarn. That's due to the manganese weathering out, pyrolusite, from the very manganese-rich pyroxene in the skarn due to this distal location. Notice the knife-sharp contact with the marble, and there's a chert nodule about 2 or 3 centimeters away from the skarn with no reaction, no bleaching, no nothing going on because of this very distal location. Okay. The skarn contact is not the limit of fluid flow, it's the limit of the stability of calc-silicate minerals. So we see lots of evidence for fluid moving past that. So the drill core on the far right, you see a little bit of distal skarn, this brown color is very manganese-rich pyroxene. And you can see these little things going off from that. Call them fluid escape structures. They quite often have a sinusoidal look like stylites. And texturally, they look like stylites, but a totally different occurrence. The stylites are a diagenetic feature of carbonates as they dewater and lithify. These are hydrothermal features of fluid leaking out away from the skarn. It's quite useful because you can map this out in the field. So if you're at greenfields exploration and you're just starting to look around things and you have a big carbonate platform, these would be your most distal indications that something's going on. So you can see this little crackle breccia up on the top. Not much going on. If you break the rock open along one of those, you can see these dendritic amorphous patterns along the fracture. And these are the fluid escape structures. They'll be very enriched in whatever elements are present in the skarn deposit. So if it's distal zinc skarn, guess what? You're going to have zinc, manganese, lead. Another thing you can do is look at the fluorescence of these. I won't go into this in detail. Fluorescence is a very complicated feature, but the manganese quite often causes a bright red fluorescence. So looking at calcite veins, not all calcite veins are equal. And so looking at the manganese content also gives you an indication of being in the distal part of the system. So these are the 3 skarn types that I've very quickly marched you through. So the tungsten skarn on the left is very deep, usually in the very lowest stratigraphic unit, the first carbonate that the intrusion encounters. And the reason for that is not coincidental, because the magma getting close to carbonates will actually cause the magma to freeze, to chemically get quenched because of the carbon dioxide forcing water to come out. So these tungsten skarns are deep. We see that in the mineralogy, the metamorphic aureole. On the far right, we have a copper skarn, much more laterally extensive, possibly in a subvolcanic environment. The skarn is much, much bigger and separating along the contact of the intrusion, quite often a porphyritic intrusion. And the zinc skarns, I've shown it here in the middle, not necessarily because it has to be intermediate in depth, but the fact that the fluid needs to get away from the intrusion and cool down before it encounters carbonate rocks. So you could have fluids sneaking away from the copper skarn on the right. You could have fluids sneaking away from the tungsten skarn on the left. The important point for the zinc skarns is they have to be distal. The fluids had to cool down before they encountered the carbonate rocks. So when I go out to a deposit, whether it's getting off my horse, getting out of a pickup truck, getting out of a helicopter, jumping off a cliff, whatever it is that gets me out to the deposit, these are the things I start thinking about. The first is the depth of formation. Okay, it should be obvious now why that's important. It's going to affect lots about the geometry, the mineralogy, and the metal content of the skarn. And the simplest thing is just to look at the intrusive textures. Is it a coarse-grained batholith? Is it a porphyritic rock? Does it have chilled margins? You can do stratigraphic reconstructions. You can look at mineral equilibria. There's lots of ways of approaching this. But I always just start with what the igneous rocks look like. They tell me a lot about the depth of formation. Temperature is obviously important relative to what metals you're going to have present. And the skarn minerals that are present, mineral equilibria, if you want to quantify that, you can look at fluid inclusions or isotopes. But if you're going to work on skarns, identifying minerals and understanding what minerals are stable at different temperatures is really important. So if you work on skarns, you become a walking database of mineral equilibria. And we like to draw all sorts of phase diagrams in the outcrops to explain what we're seeing. But you don't need to understand that necessarily, but you do need to identify the minerals. Okay, the oxidation state of both the igneous rocks and the wall rocks is really important for all the reasons I described, and that is reflected in the skarn mineralogy. So you can look at the skarn mineralogy to tell you what the overall oxidation state is, and then you can ask, is that consistent with the wall rocks I see? Is that consistent with the igneous rocks I see? And if not, that's a real big clue about where you might want to look for other types of things. Mineralogy, I can't emphasize enough. If you work on skarns, you simply have to be able to identify minerals, and mineral compositions tell you a lot. I didn't go into the details of zonation, but you can do really, really detailed stuff about where you want to be in a system by looking at the mineralogy. If I was teaching a 1-week course on this instead of a 45-minute course, I would take you through all sorts of wonderful details of mineralogy. I'm just going to very quickly jump over garnet and pyroxene. So any particular mineral has an overall formula here illustrated by A, B, and C, referring to the valence state. So the A side is +2, the B is +3, the C is +4. And you can look at what elements can substitute in there, giving you different end members for garnet. So there's 5 major species of garnet. By far the most common are the grosset or andradite solid solution, sometimes referred to as grandite. And again, that is the substitution of aluminum and iron into the B site, into the trivalent site. Okay. If you're replacing calcium in the A site with manganese, iron, or magnesium, you get what we call the subcalcic garnets. Those were those late garnet veins I showed you in the tungsten skarn that were picking up the tungsten and moving it around. So spessartine, almandine, and pyrope are the main end members. Pyroxene is a little bit simpler. Again, A, B, and C sites. The main substitution is in the B site for magnesium, iron, and manganese, giving us the diopside, edinburghite, and johanssonite end members. Okay, it's important to use these terms correctly. I don't know how many deposits I work on where they'll describe the garnet as garnet and the pyroxene they'll describe as diopside. And they'll say, do you know it's diopside? And they'll say, well, I say, no. If you call it diopside, it needs to be diopside. So let me give you an example that all economic geologists will be able to feel the pain in their bones the way I feel it when you call something diopside when it's not. So imagine your junior geologist comes up to you and says, look at this big chunk of chalcopyrite. I got a 20-meter interval of chalcopyrite. And you look at it and you go, that's not chalcopyrite, that's pyrite. And the junior geologist says, yeah, that's right. You know, it's a sulfide. You know, it's chalcopyrite. No. Chalcopyrite is a copper sulfide. Pyrite has no copper in it. This is how I feel when you call pyroxene as diopside when it's not. So if you don't know what the sulfide is, you just call it sulfide. Okay. Now you'll probably get fired if you can't tell the difference between pyrite and chalcopyrite, but that's a separate issue. Okay. But in the skarn world, you need to be able to separate what these minerals are, because again, they're going to tell you where you are and what's going on. Okay. You can illustrate these compositions graphically fairly easily in terms of ternary diagrams. I won't go through this in detail, but in a nutshell, here are the 7 main types of skarns, and this is the typical compositions of the garnet on the left and the pyroxene on the right. And individual skarns have diagnostic minerals, and these minerals tell you lots about what type of skarn it is. So if you know you've got a composition for pyroxene up here, you know it's a zinc skarn. So what do you know? It's distal to the intrusion. It's probably going to be small, but you have the potential for it being distal to a much bigger deposit somewhere. If you've got garnets with compositions up here, you know it's a tungsten skarn. And so it's going to be very deep, probably related to a big batholith, large metamorphic aureole. So all of this falls out of the mineralogy. So when you first see things in the field, these allow you to start putting things together and figuring out the zonation. And finally, this is the master diagram relating all of this together in terms of oxidation state of both the wall rocks on the left, the pluton at the bottom, and depth of formation on the right. And the reason why depth of formation and wall rock oxidation are roughly parallel is because if you're very shallow, you're in contact with the atmosphere, which luckily for us is 18% oxygen, obviously very oxygenated. And as you go deeper and deeper, the wall rocks buffer everything. So you get much more reduced as you go deeper. Okay. And if we look at this diagram, this dashed line through here is basically equal oxidation state. As we go in this direction, we're much more reduced, either because of the pluton, depth of formation, or the wall rock composition. And if we go in this direction, we're more oxidized, again, because of shallow depth of formation, of oxidized pluton, oxidized wall rocks. And then all the labels on here tell you what metals will be present, what the garnet pyroxene ratio is like, what the composition of the garnet pyroxene. So all this comes together, it gives you a little roadmap for a given deposit that you see and what you can do with it. And when you understand all this, this is your reward. You get a license plate that says Skarn, and you drive around and everybody goes, whoa, this guy must know something. So now you know as much about skarns as I do, and I'd be happy to answer any questions that you've got.
Thank you so much, Larry. That was just brilliant. I loved having you on. So thank you.